In terms of computer science, when we use the term graphs, we typically use it the way that mathematics uses graph in the field of graph theory, which is a structure built off of vertices and edges. These are slightly more complicated than your generic scatter plot or bar graph, since it's an object built off of vertices and edges in a space. And these edges can have multiple properties to connect these vertices. Edges can be directed, where the vertices connect to each other and the edges are oriented, which is one vertex has an edge that points to another vertex, or undirected. Vertices connect to each other, but the edges are not oriented, which means they just connect to each other and they don't point. Edges can be weighted, which means they have one or more additional attributes than just existing. For example, if we're talking about an airplane flight schedule, we can have the attributes, the cost of the flight, the duration, the distance, which would all account for attributes on the edge. An unweighted edge has 0 additional attributes. It just exists. Parallel edges can exist when there are multiple edges between the same two vertices. For example, we have vertex A has an edge to vertex B, and vertex B has an edge to vertex A. They go to each other, and they're considered parallel edges towards each other. Loops exist when there is an edge that connects to the same vertex from which it leaves. For example, vertex A connects back to vertex A. When using graphs in data structures and computer science in general, there are 2 main data structures that we look at when implementing graphs, and those are adjacency matrices and adjacency lists. We will start with adjacency matrices, which is kind of exactly what it sounds like. It's a matrix, which is just a 2D way of representing a graph as the matrix. It's used to tell us which nodes are connected, and it's very efficient at it. Adjacency matrices store a matrix of all possible edge combinations of an n by n matrix. This makes it easy in regards to weighted graphs, since the matrix will store the weights of the edge and not just the edge itself. Adjacency matrices are great for dense graphs. Since it has all the possible edge combinations, lookups become extraordinarily easy. And compared to our next structure, adjacency lists, adjacency matrices are very easy to implement. The edge lookup for an adjacency matrix is O of 1, which makes it very efficient as well. These benefits come with a cost, however, as adjacency matrices use a lot of memory and are very expensive to add and remove nodes for. In regards to the add and remove of vertices and edges methods, they differ from adjacency lists slightly. In the case of adding a vertex or an edge, it stays relatively the same. Adding a vertex increases the size of the matrix by 1 on each dimension, and adding an edge changes the value of the corresponding matrix value to the weight of the added edge. Removing an edge is as simple as it sounds. Set the weight of the edge back to the default, null or 0, whichever you choose. But it becomes more difficult when you try to remove a vertex. Removing a vertex from a graph, hypothetically you could just set all of the values to 0 or null. However, that wouldn't change the size of the graph, which means the graph will always just have an empty index where a vertex once was, and take up that amount of space. A much better, albeit more complicated and expensive way of removing a vertex is to copy the last vertex in the index and replace the vertex you're trying to remove with it, and then either reduce the size of the matrix or keep the final empty index as an open index for any future vertices to be added. An adjacency list, however, is a list of lists, in which each node of the list has a list of the connecting nodes. Compared to adjacency matrices, instead of storing all possible edges, adjacency lists are only able to store currently existing edges. Adjacency lists excel when working with sparse graphs, and it's much easier to add and remove vertices and edges from an adjacency list rather than an adjacency matrix, since in an adjacency list, you can just simply update the list, whereas in an adjacency matrix, the remove function is slightly more complicated than just simply updating the structure like we just talked about. When working with these kinds of data structures, and all data structures in general, there are a few handy algorithms that we typically use for searching, and the 2 that many computer science students encounter really early on is breadth first and depth first searches, and it is covered a lot again, and it is also covered quite a bit when talking about graphs. Breadth first and depth first searches are the two main elementary graph algorithms that you tend to work with while learning data structures and algorithms. Let's talk about the components of a breadth first search first. Breadth first utilizes a queue as its main data structure, where the starting node is enqueued and marked as visited as it leaves the queue. Then all of its children get pushed to the queue. Since we are marking the vertices as visited, we use a Boolean property to prevent nodes from being visited more than once, which is important as to not create an infinite loop. Depth first search, on the other hand, utilizes a stack as its underlying data structure. Depth first search strives to find all of the nodes in the deepest part of the graph by traversing the adjacent children of the starting node. Like the name suggests, it follows the deepest initial path, which means every time a node gets visited, it gets pushed to the stack and becomes marked as visited. Unlike breadth first traversal of trees, the depth first search of a graph may contain cycles in which nodes are visited more than once. This happens because the algorithm must backtrack to find where the next deepest unvisited node is. Just because the node gets visited more than once doesn't mean it gets processed more than once, however. We use that Boolean property again to prevent pushing the same node to the stack more than once.